Good morning, everyone. Welcome to this webinar about the lightweight materials deployment in electrical vehicle chassis parts. My name is Daniel Casellas. I am the Scientific Director at EURECAT, Technological Center in Barcelona. I'm also adjunct professor at Luleå University of Technology in Sweden. My background is in fracture mechanics, more than 20 years of experience in application of fracture mechanics to address lightweight solutions in vehicle parts, especially in thin sheets for the bodywork and the chassis. It's my pleasure to introduce to you this webinar. In the next 1 hour and a half, we will see some of the results of the Fatigue4Light project. This is an European project that addresses the application of lightweight solutions in chassis parts. In fact, it's one of the first European funded projects to tackle with the challenges of lightweight materials and fatigue for electrical vehicles. In the project, we look for solutions, for different material solutions, like press hardening steels, cold forming steels, or also hybrid solutions made of metals and composites. But we especially focus on fast methodologies to boost the introduction of new solutions in chassis. We know that fatigue is a time-consuming process to evaluate. So in the project, we develop methodologies to be fast but also efficient in the evaluation of fatigue. So in the next minutes, we will see some talks about this. The agenda for today is as follows, as you can see in the screen. We will start with one presentation about modeling, how we can predict the fatigue resistance, not only in specimens, but also in components through advanced modeling. Then it will follow with two presentations about fast fatigue methods. It doesn't mean that we are running at higher frequencies. It means that we are smart and we look at where we have to look to understand fatigue and predict it from the beginning. And we will close the session with a presentation about the application of all these concepts to a vehicle part. It's going to be a wheel. Finally, we will have a questions and answer session. So you can write, as we are used in this webinars, you can write your questions in the chat and the speakers will answer it. Or in the questions and answer session, simply raise your hand and you can put your mic on and your camera on if you want, and you can directly address the speakers. So we can start with the technical sessions. So the first speaker is Lucía Barbu. Lucía is assistant researcher professor at CIMNE. CIMNE is the coordinator of the project. And Lucía is also assistant professor at UPC, Botanical University of Catalonia. Too many things at the same time, but Lucía is working hard in modeling, we know. So Lucía, you have 15 minutes to show your developments in modeling.
Thank you very much. Thank you very much, Danny. And welcome to all of the attendees to our webinar. Just a small mention. Today I'm speaking in front of you as the coordinator of the project. So even though I spent a lot of years in my life working on modeling, I will be giving you a general overview of the Fatigue4Light project, just so to make sure that all of you know better how is our consortium, who we are, and what is the work that we are doing during these 3 years of project. And I will have to invite you to come to the next webinars organized by our project to find out more about the numerical modeling techniques, okay? Because I'm very anxious to share them with you. But today, general overview of the project and a brief perspective over the results that we have achieved during these nearly 3 years of work, okay? Let me share my screen. Okay, on the screen, share, good. Can you see my screen right now?
Yes.
Great, great, thank you so much. Okay, so As all of you know, we are here today to find out more about fatigue, and specifically in relationship to the Fatigue4Light project, which is focused on the fatigue modeling and fast testing methodologies to optimize the part design and to boost the lightweight material deployment on chassis parts. And I want to share with you several aspects of our project. Among them are who integrates our consortium, what are the project phases that we've been following through the development of the workflow in the project. What is the research beyond the state of the art that the Fatigue4Light project focuses on? What are the lightweight materials that we've been tackling in the Fatigue4Light project for applying on electric vehicle chassis parts? And at the end, I would say a brief overview, because the time is very short, on several results that we have achieved in the project, just to create a little bit of hype and maybe ramp up your interest, so you can join us in future events organized by the project. Okay, so as a general overview, Fatigue4Light is a Horizon 2020 project, okay? We've been funded by the European Commission with nearly 5 million euros to work during 3 years. We started in February 2021, and we will be finishing this next January 2024, okay? So we are close to the end of our project. We've done a lot of work these 3 years, and we are very happy to share that work with you today. The consortium is formed by 14 different partners. We've joined together from 4 different European countries. And the coordinator is THIMNE, the International Center for Numerical Methods in Engineering, the institution that I'm representing today in front of you. Now, our consortium is formed by 4 different types of partners. We have research institutions. THIMNE is one of them. EURECAT, the organizer of the webinar, is also a research institute. And together with RISE, the Swedish Research Institute, we are the 3 research institutions in the project. Then we have 3 universities, the Politecnico di Torino, Luleå University of Technology, and UPC. A lot of presence, or a strong presence, I would say, from the industrial companies in our consortium. We have CRF, Fiat, we have Magneto Wheels, we have ArcelorMittal, Gestamp, Hardtech, Profil Glass, Composite Service. Okay, so I would say a strong weight of industrial partners in our consortium. And we also have one standardization body, which is UNE, Asociación de Normalización Española, who is going to help us with different standardization issues that we need to tackle in our project, specifically also related to the fast fatigue testing methodologies that you will see later on. Now, let's humanize a little bit, okay, our consortium, because we are not only figures and numbers, we are people behind the Fatigue4Light project. And here you can see a brief overview of our evolution towards through the years, I would say, as we are getting more beautiful and I don't know, more wise, you know, as time passes. Okay, about the project phases that we've been passing through as we went developing our Fatigue4Light approach during these years. The first year was devoted to a very strong experimental campaign, which was focused at coupon level, okay, for the different materials that we wanted to research in our project. And here we've had some material solutions based on advanced high-strength steel, aluminum alloys, press-hardened steel, multi-material hybrid composite solutions. A lot of work we've done characterizing their performance at coupon scale in the first year. Second year, we moved to a little bit more complex problem. We went to a lab scale demonstrator where we investigated the effects of manufacturing processes on the fatigue behavior of these demonstrators, both from the experimental and from the numerical perspective. And during this time, we also worked a lot. We invested a lot of effort in the project to develop these new fast fatigue experimental methods to reduce the cost of experimental campaigns, which, as you know, for fatigue, they are quite significant. Then also at the same time, there has been a significant effort invested in modeling, in developing new modeling techniques, mainly on the part of THIMNE, of the institution that I represent, because we wanted to develop new computer simulation methods to better estimate the fatigue life of chassis components, okay? Because this would help us, would give us better information, I would say, when we need to select the appropriate materials for the appropriate applications on chassis components. And the third year has been devoted, and we are still working on this, on industrial demonstrator scale, where we want to validate all of the modeling approach and experimental approaches that we developed at this industrial scale, let's say component scale. So this is the workflow, I would say, that we have followed in the project. And what are we doing in the Fatigue4Light project, which is beyond the state of the art? Well, we have a comprehensive modeling approach where we are focusing on evaluating, of course, the fatigue performance of the different materials we have analyzed in the project. But we can't, or I would say it's not enough as what is habitually done in the state of the art in fatigue nowadays. It's not enough to only look at the fatigue behavior if you don't analyze the whole history that material or that component has passed through. What do I mean with this? I mean, when you are manufacturing a specific chassis component, there are several manufacturing processes that are going to induce on your component, on your material, some nonlinear effects. And many different types of manufacturing processes can be used. We've analyzed several of them in our project. And I would say that one of the main advances beyond the state of the art is following this comprehensive approach where we monitor damage and plasticity induced due to the manufacturing process, stamping, cold forming, punching, welding, and we take into account these nonlinear effects and we extrapolate them or we use them also to affect the fatigue performance later on of those components manufactured in that specific way. So this is what I mean with the comprehensive approach, okay? Now, what are the materials that we have studied in the project? Well, as I was mentioning, so we have advanced high strength steels, basically CP800 for application where it is not the current state of the art for those components, and also CP980 or CP1000 for applications where we want to push forward the state of the art. They are currently manufactured, let's say, with CP800, and we want to take them further at CP980. Okay, hybrid materials and stainless steels, also a different avenue that we've focused on in the project. This is metal composite sandwich materials, okay, where the outer layer was made of aluminum alloy and the inner core was made with glass fiber reinforced polymers, okay. Also, we studied stainless steels, new martensitic stainless steel, which were adapted for press hardening. Then a different avenue has been studying advanced boron steel developed for press hardening of thick sheets. Okay, so these are chassis components with quite high thickness, I would say, and they also, these press hardened steel, they have good fatigue resistance. So this is why we chose to study them in the project. And of course, aluminum alloy, as I mentioned, they are involved in the hybrid solution. We chose the aluminum alloys which have improved fatigue resistance. And of course, you already know there are some benefits when you use aluminum alloys, such as reduced cost, improved environmental profile, because they have a high content of recycled material. Okay, now a brief overview over the results, okay, that we obtained in the project. In the first year, as I said, we devoted a lot of time to a very intense experimental campaign, where we compared the behavior of the different materials analyzed through different types of tests. And here you can see 4 of them. Of course, the tensile behavior was very important for us. The local formability was also studied by means of a hole expansion test. Then we looked at the fracture toughness of the different materials and also some environmental effects studied through a corrosion test. And since I don't have a lot of time today, I just put here a snapshot, of how these different materials compare in these different tests. But I would say for us, the most important analysis was studying the fatigue behavior of the different materials in our project. And we followed different avenues for studying the fatigue behavior. Of course, we went through the conventional staircase method, the one that is time lengthy and cost consuming, as you know. And we also studied several different rapid testing methodologies, which is what you will hear about in the later part of the webinar, okay? The self-heating method, the stiffness method, and also Polytechnico Torino did some tests on very high cycle fatigue method using ultrasound machine. Okay, I won't go into more detail here because my colleagues at Eurecat, the Eurecat team is going to present later on their method in stiffness method, and also ArcelorMittal is going to present their self-heating method. So it makes no sense for me to insist here. Second year of the project, results at lab scale demonstrator level. Okay, we've chosen an L shape for our laboratory demonstrator. And on this shape, we wanted to investigate what was the effect of having polished edges, and polished holes throughout the whole geometry, or leave some parts unpolished just to study what would be the effect of this surface treatment on the fatigue posterior revolution or fatigue posterior behavior. And you can see here different types of fracture that were obtained in the laboratory by the Eurecat team, and also different types of numerical results that we've obtained at TeamNet with a very good correlation in between the experimental and the numerical behavior. And you can see just a small snapshot of crack propagation for one of the profiles done in CP800 steel. Okay, let's move on. Results at demonstrator level. Here I want to speak about the steel lower control arm. So we've analyzed this lower control arm geometry, and we focused in our project on 3 different solutions, material solutions, which were interesting to explore for this geometry. One of them was a steel version, which was manufactured in the complex phase 980, the CP980. Okay. And here you can see this demonstrator was manufactured and was tested by CRF. You can see some images of the tested demonstrator, and here you can see the test setup for studying the experimental behavior, first in the monotonic range and after that in the cyclic range. Here you can see an image of the failed component under the monotonic regime, let's say, or the monotonic test, and some images from the modeling campaign, both from CRF side and from TeamNet side, of this misuse case, as we call it. Work for the cyclic part is work in progress right now, and we will show it later on if you join us in future webinars. Okay, now about the hybrid aluminum GFRP lower control arm. This was a different version of this geometry. It was manufactured and tested at RISE, and you can see here some images of the test being performed, and also an image of the failed specimen, again in the monotonic regime. From TeamNet side, we were also involved, and we are continuously doing the modeling for this geometry. And you can see a preliminary approximation that we obtained between the numerical result and the experimental result, at least for the elastic part at this point. Okay, I want to show you just a very, very quick video, a very nice video, and you can go to YouTube and watch it, of how the hybrid arm was manufactured. Okay, this is work done by our colleagues at RISE, and it's super interesting because they created the tool also for manufacturing the component. At the same time with the manufacturing, there was a numerical analysis, of course, which was conducted to make sure that everything would end up well manufactured, I would say. And this is the final view of the demonstrator, ready for testing. Okay, let's go fast because I don't want to lose more time. There's only one, well, we have 2 demonstrators left in our project. One of them is going to be the wheel, which Magneto Wheels will present later on, so I didn't dedicate any time in this presentation. And the other one is the cross-member beam, which was proposed by Gestam Haptech. And you can see here, this is the cross-member beam, which has a symmetrical design, in between the 2 chassis beams. And here is the actual manufactured, let's say, demonstrator. Okay, since it's a symmetrical design, we only manufactured half. And you can see a brief overview of the manufacturing process with the hot stamping and the hot press here. it's a beautiful process. Okay. Now, the geometry that was manufactured with this process was later on screwed to a testing bench, and some cyclic displacements in different directions were applied to this geometry. Okay. And from the numerical side, we've also investigated the performance of this geometry. And at the moment, we are again only working on the monotonic side, with the cyclic part to be performed during this month and next month. And the results are quite interesting and promising at this point. Okay, what about the eco design assessment? Because a big part of the project has been focused, of course, on the mechanical performance of these different materials at different scales, I would say. But eco design aspects are an integral part, a very important part of our project. And on this part, we've worked a lot to rank the performance of these different materials through different aspects, you know, sustainability, recyclability, end of life aspects, in use, energy consumption, etc., etc. And all of these aspects, they need a lot of time also to be explained. So I won't have time today to share them with you, but I wanted to create a bit of interest, okay? So please join us in future webinars of our project and follow us, because we will publish a lot on the results obtained in this part in the following period. And nothing more from my side. Thank you very much for your time and for your attention. And I'm available for any questions at the end in the Q&A session. Thank you.
Thanks, Lucia, for this overview of the Fatigue4Light. Of course, more modeling issues in the next webinars. We're really we're really looking forward to hear from you in all these topics. So the next speaker is Sergi Parareda. Sergi is a researcher at the Mechanical Behavior Department at EURECAT. Sergi has about 5 to 10 years in experience in fatigue testing, and he will show us the latest developments on the rapid fatigue method. Please, Sergi, go ahead.
Thank you, Danny, for the introduction. Yes, as mentioned, I will start with the first method that we developed here in the Fatigue4Light project. I know it was already mentioned, but just to have an overview of which is the situation in the electric vehicle. Probably most of you already know that the weight of the electric vehicle due to the battery is increased in about 15 to 40%. So of course there is a need to reduce the weight of the electric vehicle and to keep it low. So a low weight will mean higher range and also maybe a safety vehicle. So if we want to reduce the weight of this vehicle, we have different strategies that have been developed for the body in white and so on. So by reducing, for instance, the thickness of the material. But also here in the Fatigue4Light project would be, as already mentioned, would we address is the chassis of these vehicles. So the aim is to reduce the weight of the chassis in about 20 to 30%, which means 12 to 50% of the weight reduction of the structural weight of the vehicle. So, but if we want to address this lightweight design, let's say, we should consider two main properties. When we are talking about these components, for instance, the lower control arm that, for instance, Lucia shown, or for instance, the chassis of the heavy-duty vehicles, we have to consider the fatigue properties, of course, due to these cyclic loads that are applied in the chassis during the utilization of the vehicle, but also for when we're talking about metallic materials, we have to consider good for mobility. So the conventional approach, let's say, is okay, we are using maybe some conventional steels or some advanced steels, but the main strategy is try to move to an advanced high-strength steels in order to obtain this lightweight design. So materials with a higher tensile strength, which is usually related to a higher fatigue resistance, and also try to keep the same elongation or improve the elongation of the material in order to obtain a good formability and obtain these components with complicated shapes, and then reduce even more the weight of the components and the weight of the vehicle. But well, fatigue, it's a difficult or complicated issue, and is governed by the weakest link. So a lot of different parameters can affect fatigue, as you know. So maybe the material itself, or perhaps some defects that we can find in the surface of the material due to the roughness, or maybe due to the joints, or maybe even due to the component design, where we can have some stress razors or different irregularities that can compromise the fatigue resistance of the component. So in order to properly design these components, it's interesting to know or to characterize the material in these different conditions. So by considering all of these different points, but yeah, as already mentioned, the fatigue tests are time-consuming and also expensive. So there is a need to obtain new strategies to reduce the testing time. As Lucia mentioned, here in the Fatigue4Light project, we have two strategies, let's say. One strategy is to use a high-frequency equipment, so we can reduce the testing time by increasing the frequency, so the loading and unloading frequency of the specimen. In this case, we can reach up to 20 to 30 kilohertz, so yeah, it's a huge reduction of the testing time. And also we can use a loading block sequence. The good point of these strategies that we can use a conventional equipment, so some servo-hydraulic machines that are common in all the laboratories, and also some extensometers and different equipment that is pretty common. And well, if we want to, but the point is that if we want to use this new strategy by using these loading blocks, we have to consider different points if we want that this approach will be accepted, let's say, and use it in the different labs. So an earlier researcher just mentioned it, that the test must be expeditious, simple, requires a minimum number of specimens, and also accurate. So by keeping all of these points in mind, we develop this stiffness method here in the Fatigue4Light project. And the method basically tries to monitor how the damage is evolving in the material. So from an initial state where we have cracks or damage, let's say, to the development and growth of these micro and macro cracks. So here is a very schematic graph of how the fatigue damage, let's say, is evolving in the material. We have these micro cracks that then coalesced, and we have this macro crack. And the idea is to monitor this damage evolution by using the deformation, by measuring the strain, and apply, while we are applying defined load sequence that we will see later. So in this case, we can easily identify the elastic stress strain behavior, where we have damage due to fatigue. Then we have this second stage where we have this small crack initiation and propagation, and finally we have this coalescence and formation of a macro crack. So the main idea of the stiffness method is to monitor this fatigue damage by measuring the strain at a given or at a constant stress value. So as you can see here in the left-hand side, we are measuring the strain for a given stress, in this case, the half of the yield strength. And then we are applying some fatigue cycles, and we are measuring once again the strain for this stress level. And then we increase the stress, the fatigue stress, and we apply more blocks. So at the end, we have, until we reach the fracture of the specimen, so at the end, we have this evolution of the strain against the for each one of these fatigue blocks. So by plotting in the right-hand side of the slide, you can see the plastic strain, which is related with fatigue damage, against the maximum stress of each one of these fatigue blocks. And in this case, we can clearly see how the strain is evolving. So the fatigue damage is evolving at a given stress value, and this stress value is the fatigue limit of the material. So, but also the good point is that since we are monitoring the fatigue damage, we can not only define the fatigue limit, so we can also define the slope of the SN curve. So we can obtain a complete characterization of the fatigue resistance in a short time. So here, just to show a little bit the results, we tested 3 different materials, the dual phase material, which can be considered as a reference. And then we tested 2 CP steels, complex phase steels, the stress ratio of 0.1 by controlling the stress. We monitored the strain by using a DIC system that you can see here in the left-hand side of the slide. We used a common load frequency of 30 Hz, so a common frequency of an SN curve, for instance, or a staircase testing, and then a block length of 6,000 cycles, so the length of each one of these fatigue blocks that you can see here in the middle of the slide. And then, well, we measured it, by using this strain, we measure it, or we monitor it, the damage, the fatigue damage that is evolving in the material, and we focused on this first regime, which belongs to the continuum damage mechanics. So here you can see some results that we obtained for these 3 materials, and also here you can see the results for different edge conditions. So when we are talking about different edge conditions, we mean that we have the hourglass specimens, for instance, and we polish the edges. So this is the polish condition. But then also we included the trimmed condition. So we mechanically shared the edges, and we obtained the let's say the well-known edge shape where we have different defects and so on. And we tested all of these different conditions for the different materials. The good point is that we can obtain the results in 2-3 hours per specimen. And here you can see the results. For instance, in the column of the left is the fatigue resistance by using the staircase method, so the conventional method. And then in the right column, we have the fatigue limit from the stiffness method. And we can say that, well, the results are quite similar, and the reduction of time is very, very relevant. So the good point, as mentioned, is that by using these methods, we can determine the fatigue resistance, the fatigue limit, but also the slope of the SN curve of different materials, but also by considering different effects. So the microstructure of the material, some defects, forming effects. We also evaluated this point of the forming effects in the project. Yes, the trimming and punching, as mentioned. And the point is that if we we are able to use this technique together with another approaches that results in an even more powerful tool. So, for instance, here we have these 2 specimens that I showed, so that corresponds to the previous results for the polished and trimmed edges. And here what we can do is relate this different behavior to the damage tolerance of the material. So also in the Fatigue4Light project, we developed a new approach where we can relate this reduction of fatigue with the fracture toughness of the material. So for some materials, for instance, in this case, for the DP material, the fatigue resistance for the polished and trimmed condition was almost the same. So there was no reduction or significant reduction. So in this case, we have this KF factor close to 1. So the fatigue resistance was the same. But then for another materials, we had a higher or a notable, let's say, fatigue strength reduction. and for instance, for this CP grade, and this might be related with the fracture toughness of the material, since fracture toughness is related to the damage tolerance. So here, as mentioned, this is the tool that I mentioned. Here we can plot the fatigue resistance for the polished conditions obtained by the stiffness method. So we can easily obtain this data as in 2 or 3 hours, and then we can also plot against the fracture toughness. So fracture toughness can be also obtained in a short time, and by plotting all of this data here, we have a chart to select the best materials for a lightweight design of a chassis components. And here, well, we just put it we define it a window, let's say, for materials with a high fracture toughness and a good fatigue resistance. And this is a point that is relevant, since, well, the materials, that when polished, everything in the lab is fine, but then in the real part, we have these defects that can compromise the fatigue resistance of the component. And this is all from my side. So thank you very much for your attention, and I will be happy to answer the question afterwards. Thank you.
Thanks, Sergi, for this the presentation. Our next speaker is Rémi Mounier from ArcelorMittal. Rémi is a research engineer at Arcelor with many years of experience in fatigue, especially in high-strength steels. So Rémi will talk about another method for a fast evaluation of fatigue. So please, Rémi, go ahead.
Yeah, I think you can see my screen. Thank you,
yes,
for the introduction. Sergi made a short presentation, an introduction to fast testing methodology, and today I wanted to make a focus on self-fitting measurements. Surprisingly, it's not something new. This method has been developed more than 1 century ago. Just to say, okay, during cyclic loading, Strohmeyer observed that during fatigue testing, there was an increase of the temperature under cyclic loading. So he determined with a device he developed specifically for the test that the temperature elevation was directly linked to the appearance of fatigue. So it was the self-fitting measurement were born. So for the principle of the test, as Sergi and Lucia said, the objective is to have a fast estimation of the fatigue properties. One test for self-fitting measurement, it takes about 2 hours for one specimen. We need a reduced quantity of material. Here you can see the geometry of the sample, and it is very interesting in terms of product development. Then the idea is to measure during the test the temperature evolution of the specimen under cyclic loading, just as Strohmeyer did more than 1 century ago. And then the idea is to directly link this temperature evolution to the fatigue properties. For one test, the configuration, we use 1 specimen, and we need 3 thermocups. 2 are fixed on the grips of the servo-hydraulic machine, just to measure the temperature evolution of the system and of the environment during the tests. And then 1 thermocup is fixed on the specimen. As we are performing self-fitting tests at the load ratio -1, we need an anti-buckling device to avoid buckling under compressive load. And then, according to the geometry of the sample, where we can consider that the temperature is quite homogeneous in the useful area, we can reduce the 3D heat conduction equation to only 1 adimensional 0D heat conduction equation directly linked with the temperature evolution of the specimen, and with ED, which is a term devoted to the appearance of microplasticity, and then to fatigue properties. So we can directly link these 2 parameters, the temperature evolution and then the dissipated energy at the origin of fatigue phenomena. Then the principle of the test under cyclic loading. Here you can consider only one cyclic loading at a loading frequency, which are quite the same conditions that Sergi is using for the stiffness method, a frequency of 13 Hz, a load ratio of -1. And then we can observe during cyclic loading a progressive elevation of the temperature up to a stabilized temperature, which is measured for each cycle. And then, as for the stiffness method, there is a stepwise loading procedure with an progressive increase of the stress amplitude during cyclic loading, with successive series of cyclic loading, and then unloading or no loading, just to permit the temperature to return to thermal equilibrium. And then for each series of cyclic loading, we are measuring the temperature evolution of the specimen. We can see here different steps of loading on the same specimen with the different evolution. And then we measure the stabilized temperature, which permits on the right to plot, which is called a self-heating curve, representing the temperature of the evolution of the specimen according to the stress amplitude. Okay, so we have one curve. So what can we do with this curve? First, as Stromeyer used more than one century ago, the idea is to use some kind of deterministic approach to determine an estimation of the mean endurance limit at 2 million cycles. Here we consider for the test that the intersection between the axis and a straight line, which is taken as an asymptotic behavior of the self-heating curve, we can consider that the intersection between these two lines is the mean endurance limit. Over the years, we have many metallic materials which have been tested, many aluminum alloys, and we know that the method is quite accurate for these grades, but only a few have been tested on composites. So one of the ideas also was to test if this method was relevant. Then for a second approach, we can use a probabilistic model, because as we know, fatigue is a dispersive phenomenon. Having information about the endurance limit is good, but we need also to have estimation of the standard deviation according to fatigue tests. So for metallic materials, we developed a two-scale probabilistic model representing a progressive appearance of microplasticity. And then we can completely describe a self-heating curve for low regimes of temperature and then for high regimes. So the temperature of the evolution of the specimen is can be decomposed in two contributions. One which is not linked to fatigue properties, which is the first one at low stress amplitude, and one which is directly linked to the evolution of microplasticity inside the volume. And then after that, with the model, and as Sergi said, with the weakest link theory, we can plot complete SNP curves according to the mean standard evolution of the fatigue, and then the standard deviation. And here on the graph, we can see the comparison between experimental curves obtained in fatigue and then in black, which are obtained with self-heating measurements. So for the comparison between the metallic materials, if I can say so, for the project, we can observe for both loading ratio at the top, it's self-heating measurement results, which are obtained with one specimen in several hours only, and then on the bottom, conventional fatigue test of the results, and we can see a good correlation between self-heating and fatigue tests, which are obtained in a very reduced time, which is what we wanted to obtain. Of course, there are some differences which are very limited according to the time dedicated to the test. So it's okay for metallic materials and aluminum alloys. Then for composite materials, the idea was to test, according to the geometry of the specimen, you can see on the top right, it's not possible for us to test at -1 loading ratio. So tests were done only at 0.1, and we can observe, as for other material, a progressive evolution of the temperature of the specimen under cyclic loading. There was a need to change a bit the condition for the test, to reduce the frequency, just to be able to not overheat the specimen. We needed also to reduce the number of cycles to reduce the damage on the same specimens, but then we were able to obtain one self-heating curve, which is quite strange here for the results. We have only, I have shown before that the temperature evolution could be a contribution of 2 regimes. For composite materials, only one is observed. It's always a power 2 of the maximal stress according to self-heating measurements. But as for metallic materials, we said, okay, why not using the same deterministic approach to determine what could be considered as an endurance limit, just dedicated to the progressive appearance of the temperature. So it is relevant, right? Because here, even if we don't have a secondary regime linked to fatigue properties, because fatigue properties are not similar, it's not the same model. We cannot use the same approximations. But here you can see on the right, on the middle of the table, and then on the bottom with the left column, that fatigue is quite relevant with the progressive evolution of the temperature. And that despite the fact that the model is not fully appropriated, because here we can consider only one regime, but here for composite materials, as we can deal with the weakest link theory, when we know that when one fiber will break, it will cause the failure of the entire specimen, and here it's what's occurring with a limitation of the value. So we can have good results for one orientation of the fiber. For the other one, there was an increased error, but we can say that this method as a first attempt was quite relevant also for composite materials. And then to conclude with, here we can say that self-heating was used for the rapid determination of the endurance limit. Here, one of the biggest advantages of the method is the reduced time in comparison with conventional fatigue tests. As I said before, there can be some mistake and some limitation, but for bare materials with a volume which is homogeneous and so on, this approximation is quite good, and especially for metallic materials on a wide range of ultimate tensile strengths. There is also a good adequation for aluminum alloys, even at the loading ratio -1. The estimation of the mean endurance limit is quite good, but we have also, as I said before, an estimation of the standard deviation, which is a good thing in terms of fatigue design for the model. And then we have tested also composite materials. We have shown that there was only one primary regime, and when we can have progressive appearance of microplasticity, there is directly a failure of the specimen. And then the estimation is quite good also for the mean endurance limit. And here I haven't presented the result, but when we compare the self-heating method and the one obtained with the stiffness method for CRG, we have quite similar results. Okay, I think that's it for my presentation. Thank you.
Thank you, Remy, for the nice talk. Our next speaker is Davide Bronco, Davide is the Research and Development Manager at Magneto Wheels. Davide has worked very intensively in the Fatigue4Light project, giving ideas and challenges for wheels. So we really appreciate this industrial commitment in the application of the new solutions. And Davide will explain some of the results that Magneto Wheels achieve at the project. So Davide.
Okay, thank you, Daniel, for the introduction. I am going to share the screen. Okay, do you see the screen, the presentation? Yeah. Okay, perfect. Very good. Okay, so a brief introduction of MW. MW is a division of CLN Group, and it is a steel wheel maker, leader in the sector for passenger car and light commercial vehicle. MW contribution to the project, to Fatigue4Light, is to study high-strength steel in order to improve the fatigue performance of the wheel. And the target is to reduce the wheel weight of 15%. What was the MW strategy for this European project? Okay, at the beginning, we made a pre-screening test, fatigue test, in order to evaluate which material can be suitable for our needs. And when we defined the correct material, we study a dedicated stamping cycles and a dedicated stamping sequence for produce the parts with this new material grade. We prepare the samples and the prototypes, and we correlate the fatigue model. And then at the end, we create a virtual demonstrator with all the concepts we studied, all the characteristics we studied during the Fatigue4Light project that include this innovation, and with the scope to reduce the wheel of 15%. Okay, at the beginning, we studied, as I said before, on the specimen, the material. We started from the flat specimen. Here in the picture is not exactly the specimen we use, just to show you the difference between the first type, the specimen we use, this Dogmon specimen. And we studied the fatigue performance of DP600 material, that is the material that normally we use for the wheel, and also other material, SLA 700, DP 800, and CP 800. Then we reproduce again the fatigue performance, the fatigue test with this special specimen. This special specimen have two important things. The first is that it is banded, and so inside the specimen is we include also the hardening phenomena that we have, for example, when we stamp the wheel. And also we convert the stress from pure traction and compression stress that we have in the flat specimen in a band stress, that is what we have on the fatigue test on the wheel. And at the end, we investigate some special treatment, mechanical treatment on the specimen. For example, we investigated the shot peening, laser peening, and in this graph we have the results with the shot peening. As is visible, the performance for the CP800 shot peened is really better comparing to the DP600 shot peened. After this test, we selected the CP800 material as a new material to start 600. sorry. Okay. This part we selected the two different case study. The first is the first reference is for the disk, so for the internal part, this part, and we make so usually this wheel has the disk, so this part with 4.3 millimeter DP600. We produce some samples with 3.7 CP800. The second case study is for the rim, the external part, and usually this part in that wheel is 3.5 millimeter, and we pass to 3 millimeter CP800. After the case study definition, we perform the stamping simulation in order to identify which was the better sequence for stamp the CP800, because the characteristic comparing to the DP600 are different. We create a dedicated tool, and then in our plant in Romania, we produce the parts in different campaign. Okay. Here we can see the results, the fatigue results on the real disk, so the parts that we produced. And in this graph, okay, we have in the blue the fatigue results for the current wheel, that is DP600 4.3. In gray is the CP800 3.7. As you can see, the CP800 comparing to the DP600 is lower as performance, but this is normal because we reduce the thickness of 0.6 millimeter. Then we made the mechanical treatment, so the shot pinning, and as is visible, the DP600 shot pinned, that is the orange one, improve the performance, but only, we can say, at a high number of cycles, so low load, changing the Euler slope. While in the CP800 improve at high load and low load, and reach more or less the same performance as the P600 for 4.3. This permits to reach the goal because we have a solution that is 0.6 millimeter less thickness, reducing the disk weight of 15%, and so we have a lighter solution. After the disk, we tested also the rim. The test for the rim are not yet finished to 100%. In any case, on the rim, the situation is a little bit different. So the 3 millimeter CP800 compared to our normal rim S235 JR has lower performance. But we can say that with this material, we cannot reduce the weight and the thickness of 15%, but of 7.5%. One thing that I would like to add is that these tests were done without the shot pinning. For the moment, the shot pinning on the rim was not investigated. So probably with the shot pinning, the performance can increase, and we can reach also for the rim the 15%. Concluding, the target for this application, we identify this new material, new application on the wheel for the light commercial vehicle, because usually the light commercial vehicle has higher load and so higher thickness of disc and rim. With the CP800, we can reduce the weight, and so consequently also the CO2. we can keep a competitive price and low cost of ownership, and also the light commercial vehicle usually hasn't particular requirements in terms of NVH or stiffness. So the comfort compared to the passenger car is a little bit less important, and this is the reason why we can decrease for that type of wheel the thickness of disc and rim. Here it is an example, an exercise that we did, which for light commercial wheel that we have in our portfolio and are high runners, so with very high volume. And we estimate the weight that we can save if we change the current material to CP800. And it's visible that the weight is a lot. And then if we consider that this is for one wheel, but on the vehicle we have 4 wheels, so we have to multiply this number by 4. And this is an estimation on what we can save in terms of CO2 per year, because for the LCA calculation of the wheel, the 90% of the contribution of the CO2 is due to the material. If we can have less material with CP800, we can save this value of CO2 per year. So from my side, that's all. Thank you.
Thanks, Davide. Nice ending of the presentation with the CO2 footprint and the sustainability. We always have to keep this in mind for material development. So now it's time for the questions and answer session. So I would like to ask to the speakers to put the cameras on. And we're going to start with the questions that are from the chat. So one of the questions is that is from Arturo Casillas, and he's asking if there is any relation between fatigue and friction during sheet forming process. Probably he's interested in understanding the effect of lubricants in forming. Maybe Sergio, do you want to say something?
Yeah, absolutely. Yeah, thanks for the question. As I mentioned it in the beginning of the presentation, so we know that fatigue it depends on a lot of different parameters, and one of these parameters is the surface condition of the material that we have, and also which is the condition or the defect that we can find in the shared edge, for instance. And well, here of course, if we can use or we enhance the sharing processes or the forming processes by using lubricants or different tools, or somehow we can increase or enhance the process. Of course, this will have an impact on the fatigue resistance, and we will obtain a higher fatigue resistance of the material if we have a better surface with less defects. So
yeah, something to add from the other speakers? Okay, the next question in the chat is about the shot pinning effect. Why it has different effects on fatigue for wheels? This question is for Davide. And before answering, Davide, please, this is a question in the chat that if we are able to use microphone, yes, after this answer, please raise your hand and you can put the mic on and the camera on if you want. So please, Davide, if you want to discuss this question.
Yes.
The question, sorry, is from
I'm not.
Aitor Ortaza. Sorry. Please go ahead.
Sorry, I didn't catch. Sorry.
No, please go ahead.
Sorry, I read the question in the chat.
Yep.
Yes.
Yep.
Okay. Yeah, I'm not expert on the material, but what I can say is that the DP600 is a dual phase material, so has just 2 phases, ferrite and martensite. and the shot pinning is more impacting on one of these two. The complex phase has more phase than these two, and so the contribution of the shot pinning is higher than the dual phase material.
Yeah, I can add that in high strength materials, the shot pinning effect is higher because it's related to the yield stress of the material. And it's interesting what you said, that dual phase is a multi-phase material with soft ferrite and hard martensite, and complex phase is a complex phase with more finer microstructures, and probably the residual stresses are better distributed in the microstructure. Remy, something from Arcelor?
Thank you.
Yeah,
you want to comment on this?
Yeah, for the CP, as you said, the idea is to have more residual stresses for this type of grade in comparison with DP600. But that's why fatigue performance are better according to the increased compressive residual stresses.
Right. So I expect that it will be even higher for press hardened steels, Remy, or for very high yield stress materials.
Can I add some comment on these questions? I think
yes, please.
the very
your name, please.
Yeah,
your name.
Sung Jin Lu from Jaguar Land Rover. I'm a specialist in fatigue, in charge with the fatigue lab here. Well, basically, I think the question basically asks the why is difference effect for the short pinning for the DP600 against the CP800. I think the most likely, if you think about why the short pinning increase the fatigue behavior, is basically you add a compressive the stresses on the surface of the stresses on the material that will take away some external load. So you reduce the external load. However, with the when I see that curve is basically for the DP600, it may actually at higher load is already plastic deformed. So the effect from the short pinning is going away because with the CP is still elastic. So that's why it's increased the fatigue behavior. But if you're looking at the curve at a lower load, and the DP600 also increase the fatigue life. So basically, I think this is the answer for it.
Exactly.
Thank you.
The question is that you are right. This is what we are discussing in the project. That dual phase has ferrite, soft ferrite, and hard martensite, and probably the ferrite is so plastically deformed because of the pinning. And then this can be good for high cycle fatigue, but as you said, can be detrimental for low cycle fatigue, as can be more damage. And that clearly shows the benefit of higher, very fine microstructure as the complex phase materials has. So thanks for the comment.
Well, the other question, if we raise the question, should we focus on each presentation or we just
please go ahead. We have 20 minutes for discussion.
Yeah, I have a list of these the questions.
Okay.
During this, I just write down all of these things. The first is to the first presentation. There's a material characterization method. When you're actually saying you have the first step is getting the material behavior, and then the second step is looking at the L-shaped, the pseudo components, we will say, and then you go to the components one by one. So with the first step, which fatigue tests you have conducted, is that a stress life or strain life or something different?
Okay. So in the first experimental campaign conducted at material level, we were focusing on high cycle fatigue. So we did stress number of cycles. Okay.
Yeah.
And we investigated through all of the different approaches, both the rapid fatigue testing methodologies and also the conventional staircase method. Yeah.
Yeah. Okay. So for the L-shaped test is same. So
yeah.
what is the R value you use? Stress value.
Okay.
Stress ratio.
We used -1, if I'm not mistaken. Sergio, you can correct me to the experimental campaign.
Yeah,
what I mean, yeah, -1.
Yeah, okay, that's fine. Thank you for this one. And the second presentation, I think this is go to the Sergi.
Yes.
About the first one is when you're talking about the very high cycle fatigue ones. I think I had a lot of discussions with the different people and suppliers of the equipment, all these. I think the very important thing nowadays, the people is just trying to sell that equipment to you, saying, "Oh, we can reduce this, whatever." However, I attended one of their seminars. We discussed this very importantly. With the very high cycle fatigue, the specimen, if looking at the failure mode, all the failures coming from the center of the specimen, and all the tests, normal fatigue tests, the crack is always coming from the surface. So fundamentally, the mechanism is different. So you can't actually say, yeah, well, we'll use this. Yes, I think this is a fundamental thing. If you don't have the same failure mode, you can't use it. So this is the question one. And then the second thing, when you're actually talking about the stiffness, I think one of the curve you plotted out is the stiffness against the plastic strain. Am I right? Yeah. So,
yeah, we plotted the plastic strain against the stress in order to obtain the fatigue limit.
Yeah.
And also
however, however, if you think about when you actually doing well, for your test conditions, you are running R equals 0.1. That means tension.
Absolutely.
Okay, in that case, you only have your first loop have the plasticity, and after that is elastic. So you can't actually differentiate that unless you test minus, you have some compressions, then you have the plasticity with it. Otherwise, you only looking at, because if you think about it, if loading to the after yield, and then if you unloading to 0, it's like a straight line. It doesn't give you the further plasticity. So that's the question on that. And why actually using this one to get some material output? So what is the output for CAE? Is that the endurance limit?
Yeah, exactly. So here, well, you know, you're right. I mean, when we are testing the material at different stress ratios, it's clear that when we have this -1, we are also inducing maybe some more plasticity, but also at a smaller scale level, of course, we have plasticity. So this is how fatigue evolved, right? So here what we are comparing is including these different plasticity effects like ratcheting, or well, these different fatigue modes that it can be developed in the material, and then we are seeing how this micro damage that we call it plasticity in order to define a variable that it's understandable for everybody. But of course, inside this plasticity level, here we have discontinuities. So we have micro cracks. We have, of course, this microplasticity. We have a mix of everything. It's very difficult to separate everything. And then here, what we focus on is to detect when these micro cracks are evolving in the material. Okay, so at the end, we are comparing the initial deformation for a given stress level. And then if you have this microcrack, this plasticity, and well, a lot of different discontinuities that you have there, then this plastic behavior or this strain behavior is different. And when we identify that something is happening in the material, we are correlating this data, these strain levels with different features. In this case, we did a lot of work relating this strain measurement with microcrack propagation, and we are using these points to define the fatigue limit or the endurance of the material, and also we can use this data to obtain the slope of the SN curve. So there is a lot of work behind. We can share with you some papers that we have relating all of these different strain measurements with all the phenomena that is happening in the material, and of course we can continue this discussion wherever you want, of course.
Yeah, with this one, when you get the endurance limit from there, what is the R value for that endurance limit? Because you tested a different R on your test.
Yeah,
so endurance, yeah, because the mean stress is a fundamental for the fatigue life damage calculations. So when you're actually saying, yeah, we have the endurance limit at what R value?
This point is at 2 million cycles. So it's let's say for this stress ratio of 0.1, but also we tested for different stress ratios of -1, or I mean the one that we want to evaluate. And usually we are talking about the million cycles, so 1 million, 2 million cycles. That's a conventional number of cycles used in the automotive industry and, well, in the engineering, let's say, right? So
but the thing is, when you actually run your test, you run a lot of different R values in there, and then when you get the final result, which R value is equivalent to for your endurance limit? Is that particular at particular R equals something? Or
yeah, exactly. I mean, at the end, the stress ratio is constant in throughout the test. I mean, we are always using.
Do you use the last block R values? To define the endurance limit.
Yeah.
Okay, so that's the clear. So basically, the other one is when you're talking about the fracture toughness stuff. The fracture toughness is mainly dealing with the elastic, but in chassis components, the chassis. So that's the question I'm trying to put a big effect here. In chassis, particularly when you're dealing with the electrical vehicles, you got a huge battery applied to that. It's a huge load applied to chassis. The chassis is always elastic plastic and huge plastic sometimes. And then if you actually using that, how do you account to delta K? Do you use delta J or delta G?
No, this is another approach. I know that I just mentioned fracture toughness. It's a simple word, but a complicated word, you know. And of course, here is not a fracture toughness in terms of delta K and so on. It's in terms of essential work of fracture. So it's more related to J integral. And of course, it's elastic plastic. And then here we just wanted to show how this fatigue resistance is decreased for some materials, and this is related with the fracture toughness in terms of elastic plastic behavior due to you have small micro cracks that are introduced, for instance, in this case, in the trimmed edge, and these micro cracks are in the elastic plastic regime, and then this is why we are using this fracture toughness approach to select the proper material, okay, for these applications, and to explain why we have this different behavior for apparently the same materials, but well, with different fracture toughness values and different fatigue resistant strength.
Okay, yeah, I understand that you are trying to using the threshold value, and then to at early stage of selection of materials. Yeah,
exactly.
You really need to consider in the plasticity applied to that.
Absolutely.
Okay.
Yes.
Thank you for your answer.
Thank you.
The third one.
Thank you. Yeah.
I got a list of this. Sorry about that. The third one is Remy about the self-heating test.
Yeah.
So the temperature, when you're actually using that one to measure the temperature, have you seen the effect of the environment? For example, if you're putting a large anti-buckling guide there, So actually, the anti-buckling guide will change the heat transform.
No, the idea is to limit the friction with thin Teflon sheets, so there is no overheating. We have tested on thicker specimens that there was no impact of the anti-buckling device.
Yeah, I just thinking about the so well with this one, the end of result is the HCF, isn't it?
Yeah,
high cycle fatigue ones.
Exactly.
Yeah. Okay. The comment on your polymer stuff. So we have actually conducted a lot of things on polymers. So I published the paper on 5 years ago regarding this. Very important for your method. For the polymers, the material fatigue behavior is dependent on the temperature.
I agree.
If you change your temperature, it's unlike metal. In metal, if you say, okay, I run this at 1 hertz and 20 hertz, 30 hertz, no problem at all. But with the polymers, I think there's the maximum you can apply to
this one,
at the long high cycle regime is 5 hertz.
Yeah,
if you actually increase everything changes, the behavior change, you can't actually, you don't know what you're testing. And then also if you increase your loading at lower live regime, and then probably you can only test 2 or 3 hertz for that. So this is just a comment.
Yeah, I agree with you, but here we have tested for each case. Our objective is to limit the temperature elevation of the specimen, to limit the impact of the environment. And for people who are testing polymers, it's the same. You're right, you need to limit the frequency to be able to have something which is representative to the material behavior.
Yeah, I think that there's a European, it's quite big project. It's called Compass. It's working on all the polymer stuff. So it's across a lot of the labs. So we have attended that project as well. So okay, so that one's for you. Thank you for your answer. So basically, I think I mentioned something for the last Renko about the wheels.
Davide, yes.
Yeah. The test, the fatigue test. So what is the R value where actually you tested it? This is only question.
R minus 1.
Because R minus 1.
Yes, because for on the wheel, one of the tests is not the scheme of the test is not presented in the presentation, but is the bending test, and it is alternate bending moment, and the fatigue is -1 because it's symmetrical on the wheel. The stress map is symmetrical on the wheel.
Yeah, that's good. So the other question, I think I have already mentioned, is the short pinning stuff. Okay, thank you. I think I talked too much.
No, thank you.
Thank you.
Very nice.
Thank you for the interest out of the consortium partnership. So that's nice that you can give us fresh questions. There are still some more questions in the chat. One is about it's from Julian Avila. Remy, I think it's for you, asking for papers for the method. I mean, I think it's easy to answer. And for Sergi as well, the DIC system you use, Julian is asking if the DIC system can work to properly measure the strain fields during the fatigue test, or do you interrupt the test and measure?
Yeah, this is a point, relevant point. So you know that to measure, in this case, the strain by using the DIC during the fatigue is, I mean, it's very difficult. You need a DIC with high-speed cameras. In this case, this is why we developed this method, and we stop, let's say, or we measure the strain only at these different loading and unloading steps between each one of these fatigue blocks. So in this case, the loading and unloading step is slower, let's say, than compared to the loading and unloading frequency. And this is why we can use DIC system, a common DIC system, and avoid the utilization of a DIC system with high speed cameras. And maybe, well, but the point is that we can use the DIC system, but we can also use a conventional extensiometer attached to the specimen, and then it's also easier to obtain these strain measurements. Okay, so you know, we developed this method in order to this way that can be used by using all of these different strain measurement sensors.
Yeah, I think we can upload the papers in the Fatigue4Light website.
Absolutely.
If not, because then I kindly ask to the one that is interested to go to visit the website and look at the papers we have, or contact us for any other question. And the last is still about the shot pinning. Just to finish this, David, Aitor Ortázar is asking about microloy steels, why they have different behavior, even the yield stress is similar to complex phase.
Yeah, we did investigate so much that type of material because after the first step of screening, we saw that also in the band specimen without the shot pinning, the performance are not so good because the hardening phenomena will not improve the performance like in the DP600. And then when we made the shot pinning, we observed a really big improvement on the CP800 and not on the other material. So we decided to go on with the CP800, and we didn't investigate so much the other two material. Maybe we can do in a second step out of the Fatigue4Light project.
Remy, any idea about this?
I think it might be due to the evolution of the yield surface, according to the difference for HSLA and CP800. I think the evolution of the yield surface after shot pinning might not be the same for both products.
Probably like this.
Mm-hmm.
Okay, if there are no more questions, I would like to thank all of you for the participation, for the speakers, for the nice presentations, and for the audience for the interest. I see that there are more webinars about eco design also from the Fatigue4Light project coming up. So now Miriam is putting on the chat. So hopefully we can see again on the screens in the coming days. So thank you again. Have a nice day.
How can we get the recordings? Are you going to send these recordings?
Yes.
After
Yes.
that? Right.
Yes.
Great.
Yes.
Okay.
We will have everything will be available.
Excellent.
Thank you so much. Perfect. Have a nice day.
Thank you. Bye bye.
Thank you.
Bye, everyone.